Okay, welcome to the second half of electrostatics. The first half of electrostatics we looked at electric field and electric forces. In this half we're going to look at the energy associated with electric fields and forces, and to do that we need to introduce the concept of the electric potential. This is not the same thing as potential energy, but it is a closely related concept. So to illustrate what I mean by electric potential, imagine that we have an electric field in some region in space. And also, let's imagine that we have a point charge, which I'll assume to be positive, that we move from some initial position to some final position, so that it has displacement delta x. Now the question is, how much work does the field do? To do that, we need to understand what work is. Remember, work is equal to F dot delta x. For an electric charge in a field, the force is equal to QE. So that means we can write the work done by the electric field as Q times E dot delta x. Notice in this case that that will be negative. Because the angle between the force and delta x is going to be larger than 90 degrees. Also remember the definition of potential energy. The change in the potential energy of a system is equal to the negative of the work done by the field. So the change in potential energy as we move the charge from initial to final positions is negative QE dot delta x. And now what we'll do is we'll notice, okay, if we double Q, then we're also going to double the change in energy. And if we make Q smaller, we're also going to make the change in energy smaller. So if we look at this quantity delta U over Q, that's going to be a constant, or it's a constant ratio. And it's equal to negative E dot delta x. And this quantity we're going to call the change in the electric potential. So this is something you should memorize. There's two equations here. One is for a constant electric field. And the other one is for an electric field that is not uniform. So it's the integral form of it. So V is the electric potential. Some things we can learn about it. It is a scalar, and the units are joules per coulomb. So memorize those equations, know how it is defined. This is the definition of electric potential, negative E dot delta x. Another way of expressing it is potential difference is the work done per unit charge. And this is the work done by an outside force, which is the same thing as the negative of the work done by the field. And typically we'll pick V equals 0 to be at infinity. So that means that we can assign a particular electric potential to every other point, assuming that when you're far away from all other charges, V is equal to 0. So pretty straightforward. Now an example here, which is a fairly tricky one, you've got a Geiger counter, which is a metal cylinder 2 centimeters in diameter, with a wire strung down the middle of it that's very small. And the potential difference between the wire and the cylinder is 850 volts. So the question is, what is the electric field at the surface of the wire? By the way, volts is a joule per coulomb. And so we want to find the electric field at the surface of the wire. So the first thing we remember is, okay, we have cylindrical symmetry, and given the definition of electric potential, we first need to determine an expression for the electric field. So we're going to have the outer shell, which is radius R2, the inner shell, the inner wire, which has radius R1, it's very small, and we're going to draw a cylindrical Gaussian surface of radius R without a subscript. Now the enclosed charge is whatever the charge density is on the wire. Well, actually I'll just say that the enclosed charge is Q. It's the charge on the wire. No, it does need to be. No, I can do this. And the flux through the surface of the cylinder, E dot dA, is equal to the surface area, 2 pi RL, times the electric field. Now what Gauss's law says is that the flux through the loop is equal to Q over epsilon 0. And so the electric field is equal to 1 over 2 pi epsilon 0 times Q over RL, where R is the radius, L is the length of the Geiger counter, and Q is the total charge on the wire in the middle. Notice that we don't care about the charge on the outside cylinder, because it is not enclosed in our Gaussian surface. And you're thinking, okay, that's wonderful, but we don't know what Q is, we don't know what L is. So how do we get those? And for that we need to use this idea that the potential difference is 850 volts. So we'll look at the potential difference. Potential difference equals negative of the integral of E dot dx. And in this case, we'll say that dx points in the R direction. So the dot product goes away, and we can pull all the constants out of the integral. Q over 2 pi epsilon 0 L times the integral of 1 over R dr. And really, for this problem, we can get rid of the negative sign because this is the magnitude of the potential difference. We don't really care about it. When we do that integral, and we're integrating from the wire to the cylinder because that's the potential difference between the wire and the cylinder, so we're integrating from R1 to R2. A bit of calculus here, we have Q over 2 pi epsilon naught L times the natural log of R evaluated at R1 and R2, which in turn equals Q over 2 pi epsilon 0 L times the natural log of the ratio R2 over R1. Okay, so far so good. Now we're still looking for the electric field at R1. But notice that we know that everything in here is a constant. And so I'm going to actually go to another page now. I'm going to say, but we know that 850 volts equals Q over 2 pi R, no wait, not 2 pi RL, 2 pi epsilon naught L times the natural log of this ratio. And that means that this quantity, Q over 2 pi epsilon naught L, which is the unknown bit that shows up in our equation for electric field, is equal to 850 volts divided by the natural log of R2 over R1. And so we can plug that back into our expression for the electric field. The electric field, remember, was Q over 2 pi epsilon naught L times 1 over R. So that equals 850 volts divided by, since we're finding the field just outside the cylinder, it's at R1. So R1 times the natural log of R2 over R1. Plugging in numbers, R1 is the ridiculously small number, 6.5 times 10 to the negative 7 meters, times the natural log of R2, which is 0.01 meters, divided by that very small radius. And this works out to be 1.36 times 10 to the 8th newtons per coulomb. And one interesting thing here, newtons per coulomb equals volts per meter. Those are two different units for the electric field. So that was a fairly complicated problem. The centerpiece, though, was finding out getting the electric potential in terms of the charges involved. For tomorrow, I'm going to check question 1, also problems 2 and 6. Be reassured they are not as tricky as problem 7.